So we mentioned in the previous lesson that most of that stuff in 10-1 was elementary geometry or elementary math, and we talked about circumference and pi and all those things. And so now we're going to move away from the elementary and more toward the high school aspects of geometry involving circles. And so today we're going to be talking about the central angles, major arcs, minor arcs, semicircles, and finding their measures, and we're going to talk about arc length. And arc length is different than an arc measure, and we'll try to make that pretty obvious to you as we go along. Arc measures, well, it's a really different thing. So we'll talk about it when we get there. A central angle is just an angle that has its vertex at the center, okay? And then an arc is just a part of the circle. You know, like this would be part of the arc, or this would be the whole arc, or the whole circle. And so we can look at that in pieces and parts. And we know there are known relationships we're going to study here about angles of a circle and the arcs of a circle and their measures. I will remind you that all the way around a circle is how much? 360 degrees. So it's pretty much understood that that's the way that it works. The angles of a circle have to add up to 360, these interior angles, and the arc measures have to add up to 360 because that's what it is all the way around. So there's a one-to-one relationship between the central angles and the arc measures. So let's look at this nice little pretty problem right here, and let's talk about it. It says find the value of x. And when you look at this problem, for most of you, you look at that and you're like, oh, I don't know, I couldn't find out. You can't unless you know what you're doing and take your time, think about it a little bit. But it says find the value of x. So I'm going to do something here, and I'm going to say, you know, this is a diameter, goes through the circle, so that means these have to add up to 180. It's half a circle, semicircle, which is 180 degrees. If all of it's 360 and half of it is 180. So you can see how we carve that out. Now I can say that that plus that plus that equal 180. So I'm going to go 8x and 13x and 5x makes 26x, I believe. And then a minus 4, a minus 3 is minus 7, plus 5 makes a minus 2. So when we do a little bit of arithmetic here, a little bit of algebra, I guess, you add the 2, and then you divide both sides by 26, and that ends up being 7, I believe, 7. Now one of the things that you could do real easily is put the 7 back in here and see how these things all work out, and then you would be able to confirm that it really did add up to 180. So put the 7 in there, it's 56, makes that 52. Put the 7 in there, it'd be 91, it'd be 88. Put the 7 in there, it's 35, it'd be 40. And if you add those together, you get the 180. Nice. You could even put that over there and see that it's 140. And then you would know the measure of this angle, even though it wasn't even given in terms of algebra. But if that's 140, then this one is 40, and that makes 360 all the way around, 180 for the half. And so you can see how you could take these things and just keep knowing and doing and working. And that's the beauty of these relationships. We'll say something about that in a couple of more lessons. It says the sum of the measures, so that's what they did, 180. They got the same thing we did, the 7. And so there's more of these problems, but they're the same problem pretty much. We know this is a diameter. We know those 3 have to add up to 180. 2 of them are given in algebraic form. One of them is not. But we'll be able to say that 12x and then the 75 would be 70 plus 72 is equal to 180. So 12x is equal to 108, I believe. So x is equal to 9, which is answer A. Again, we could have checked and so on. So this is how that's working. Now, in talking about arcs, we mentioned in the first slide, we didn't make any deal of it, but we have minor arc, major arc, and then we have the semicircle. We've talked about semicircle already. But the minor arc is the shortest arc connecting two endpoints on a circle. A major arc is the longest arc connecting two endpoints on a circle. And if we've got this picture here, which is the same picture, except this arc and this arc are different as far as the pieces and parts. But both of them involve A and B. So if you want to know the short one, you just call it the measure of arc AB. See the little arc symbol, arc AB. If you want to know the larger arc or the major arc, then what happens a lot of times, you put in this third point that's on the way. So you're saying start at A, go through D, and get to B. And that's how you know which arc you're talking about. So you'll see here a little cute thing. So let's just pretend for the sake of discussion that this arc right here is 100. Well, if that arc's 100, then this arc down here is 260. How do I know? Because in all, they have to add up to 360. That makes sense? Hopefully it does to you. And as we already said, that's 180 because there's 180 degrees in a semicircle. The measure of the arc's 180, the measure of this arc's 180, makes a measure all the way around of 360. It all fits. Math is beautiful. All right, WC is a radius. Segment WC is a radius of circle C. So we know that's a center. We know that's a radius. Identify arc XZY as major, minor, or semicircle. So XZY, it's a semicircle, right? It's a semicircle because its endpoints are a diameter. So it says, then find its measure. Well, its measure would be 180 if it's a semicircle. So, there we go. Another problem here says WC is a radius, same instruction. It says identified arc WZX. So WZX. It's a minor arc, isn't it? I mean a major arc. It's a major arc. WZX. It's major. It's not the shortest, it's the longest distance between those two. It says then find its measure. Well, I want to find out the measure of this arc. Since I know this is 90 right here, we'll talk about that. But since I know this is 90 and the whole thing's 360, then this piece here is 270. These are just more of the same. Here's the XW, which is just this little minor arc here, but it's 90. And we'll talk about that a little further shortly. But it's 90. And these things just keep going. It's more of the same, just practicing these same concepts. Let me move along here because we want to get to this little theorem. It says in the same circle or in congruent circles, two minor arcs are congruent if and only if their central angles are congruent. So angles 1 and 2 are congruent. Then what we know is this arc is congruent to this arc. In the same circle, that's how that would work. And we've got the if and only if, which means it works both ways. So if we have the two angles congruent, then the two arcs are congruent. If we have the two arcs are congruent, then the two angles are congruent. It's the theorem and its converse. Remember converse, the flip? Remember that? Okay, so that's where you can say, okay, then if the arcs are congruent, then the angles are congruent. We can use that to do all kinds of cute things. Y'all remember seeing pie graphs in your elementary math, so I'm going to skip through that and get to arc length. That's the last thing we're going to do here in this particular piece. That's kind of obvious. You add two arcs together, then it's the sum. I think that's pretty easy. But I want to get to arc length because that's the big piece of this lesson, is the arc length. Here is arc length. So arc length. Now, the arc measure and the arc length are two different things. Let me just show you here in this picture. We have two concentric circles. They share a center, right? Now, if this is a 90-degree angle, then this measure is 90 and this measure is 90 because the central angle is the same as the arc. The arc is the same as the central angle. So the measure of this arc from here to here and from here to here are both 90. But those are obviously not the same length. They have the same measure, but they're not the same length. Look at it, think about it. Right. Okay? So we're talking about arc measure, they're both 90. We're talking about arc length, they're different. They're obviously different. So we have this arc length formula, which you can use this proportion. I prefer the equation. I call it the part of the whole thing. The part of the whole thing. Because this angle measure in here is part of the whole 360. And then the 2 pi r, you might recognize 2 pi r as just the circumference. Because when you're talking about the arc length, you're talking about the length of the arc of the circle, which is called the circumference. So what you're saying is we got the whole circumference, but we're only going to be using part of it because we're not going all the way around the circle. We're only going to go from here to here as defined by the angle. So this little formula is going to be a friend. Now, it's not one of those things that we would have had on our formula sheet for an SOL test or for an exam. So it's one of those things you just kind of got to remember. But it's the part of the whole thing. Part of what whole thing? The circumference. Why? Because we're talking about the length of the arc, which is part of the circumference of the circle. Now, I make a big deal about this because there is a twin cousin that we're going to talk about later where we do another thing with the area of a sector, and it's almost the same exact formula, but just a little different because area, we're not talking about circumference, we're talking about area. We'll see that later. So that's the application here then will be something like this. So they want to know the length of this piece here. Now, obviously, the bigger the radius, the bigger the arc, or the longer the arc. The arc length changes based on that. So they've given us, I've given you this formula here where I just use this L as the arc length. And then I just plug the people and the stuff in the places where they go. So it's 2 pi. So you can see I need the x, which is 40, to measure the angle, 40 out of the whole 360. That's what we're dealing with here. And then the radius, which is 4.5. Then it really just be a matter of plugging it all in the calculator. That's all you got to do, plug it in the calculator. So you could use the fraction button to do that and put in times 2 times pi, the pi button, or you could use 3.14 times the 4.5. And when you do that, you get pi. It wouldn't say pi on your calculator, but that's what you would actually get. So it is 3.14 as a rounded answer, and it is centimeters. So we do another problem. It's the same setup here. You just got to put the angle measure where it goes and the radius where it goes, and that's it. That's all you're doing. So the angle measure is 28, and it's 2 times pi times r, which is 6. So you plug all that in the calculator, and the calculator is going to pop you out an answer. You round, and it's 15.92 centimeters. I would tell you one thing you got to watch for here is, so this is a similar problem. It's got the same radius, but you're talking about a different angle because we're talking about a different arc. You want to know the measure of a different arc than we did in the previous problem. But one of the things you got to watch out for here is if they give you the information of a diameter, don't plug the diameter in the formula for the radius. So you want to take half the diameter to know the radius. But they didn't do that in this case. I'm just saying that's one of the things you'd want to look out for if you're doing actual problem solving. So the arc length and, let's see. Just find the length of JL. JL. That's the same. You're just dealing with arc length. I just don't have the formula here. Remember, arc length is the part of the whole thing times the circumference, 2 pi r. Or you could use pi d if you prefer. I just didn't see any advantage in this particular case to doing that. But really, all this is circumference, okay? Just circumference. And I believe that pretty much settles it.